A potential difference, delta V, is applied to a copper wire of diameter d and length L. What is the effect on the electron drift speed of doubling delta V, doubling the potential, doubling the length, and doubling the diameter? Yes. All right. So this question is fairly straightforward in terms of getting the right answer. So it's basically just a formula. And there's a little bit of nuance, though, underlying this that is worth considering. So the formula for drift velocity, and one of the big ideas here is science really doesn't deal with reality. It's all about modeling reality so that you can predict reality and then control it, bend it to your will. And that's more of engineering, but you get the idea. And so there's different models for different situations. This is one of those examples where it's worth understanding the nuance. All right, so here's the formula. This is mass, and specifically it's molecular mass of a molecule measured in kilograms. This is conductivity, which is the inverse of resistivity, which also uses the symbol rho, which is different than this symbol rho, which is density, mass divided by volume. This is voltage. Voltage is always a difference, this is why we have the delta. This is charge of an electron. This is the number of electrons per atom. And then L is the length of material that we're looking at. So I'm just going to rewrite this real quick as M sigma delta V over rho electron charge free electrons over L. And the reason I did this is because that way I basically just isolated the things we know we're going to have change for the problem, delta V and L. And so first thing we're going to do is we're going to double the voltage. So doubling the voltage is going to double the drift speed. So for A, it's going to double. Because we have our delta V here, we double that, it's going to double. For B, we're going to double the length. Length is on the bottom. It's going to cut it in half because voltage of drift speed. Gotta make sure I don't get those confused. Drift speed is going to be proportional to the difference in voltage over length. So if we double length, we half the drift speed, and then doubling diameter. Diameter doesn't matter, so because it's not in the formula, therefore no effect. So looking at this from a more reasonable, logical point of view, we should draw a picture. So we have a picture. We're going to have a battery, looks like this, and this battery is going to create a voltage at delta V. So this will be plus, this will be negative, and between here is going to be our copper wire. We're going to draw, let's say, an electron right here, and as this electron moves from right to left, that's going to be the drift velocity. So drift velocity is just how fast the charge carriers are moving. So when you see this, your first intuitive thought is, oh, I totally know how to do this. What we do is we say, all right, this is basically a parallel plate capacitor. It's creating a uniform electric field from positive to negative. That electric field is going to create a force equals Q times E, electric field. Going to create a force on the charge carrier. That force is going to be mass times acceleration. Acceleration equals charge electric field over mass, therefore Kinemax equations. And that's reasonable. And so if we wanted to model this in another way, this would just be kind of like projectile motion. You have a ball, you hold it, you drop it, it falls to the ground. That's the same idea as the electron moving from right to left. Now, when you do this, when you plug this idea in, you don't have a drift velocity because you have a constant acceleration. Your velocity in this case would be acceleration times time plus whatever its initial velocity is, kinematics equation. And so there's no constant, it just keeps going up. That's not what's happening. The model we're going to use, the conceptual model we're using here, is going to be basically like a skydiver. So you have like, I don't know, an airplane. Is this an airplane? Airplane. Someone jumps out of it with a parachute and they fall down. And the idea is there's going to be, we'll do a free body diagram. We have mass times gravity pulling the skydiver down. And we have some sort of drag, I'll call this force drag, pulling him up. And when those two balance out, you get what's called terminal velocity. Basically, he's not going any faster because the drag, wind resistance, is going to be dependent on how fast he's going. And at some point, everything balances out and it's fine. That's effectively what's happening with the drift velocity here. So you have to think of drift velocity in terms of the resistance to flow. So then you're like, well, what about like a superconductor? No resistance, R equals 0. How fast is drift velocity? Well, the model really doesn't hold up for that because if you look at this up here, that basically means resistance equals 0, conductivity is 0, or conductivity is infinite, and we go with our velocity drift here. That basically means that this sigma, this conductivity, is infinite. And then you get infinite drift velocity. They're like, what? How can that be even faster than the speed of light? Craziness ensues. So different models for different situations. So this is pretty much normal life. Nothing crazy, no superconductors. And we're modeling the flow of electrons in this with basically a drag force. This drag force is preventing the electron from basically reaching the speed of light, which is why we get really slow drift velocities. A lot of that comes from like interactions with the molecules, imperfections, lattice work, boundaries. So that's the idea of the two models. The one model is projectile motion in a vacuum, constant acceleration. The other model is skydiver jumping out of an airplane. You reach terminal velocity, at which point you maintain a constant. This will be velocity, time, jumping out of an airplane. Reach some sort of terminal velocity and hopefully have a gradual parachute open before you reach the ground. So this part right here, terminal, I know, terrible handwriting, but I'm saying it so you know what I mean. Terminal velocity, which is the same as drift speed. Exact same concept. So sometimes it's better to model acceleration as constant. Sometimes it's useful to model a drag force, which limits your maximum speed. So that's the idea here. It might be worth memorizing the formula if you have a test coming up. Otherwise, just briefly kind of understand the concept of what's going on, and then pull up the formula when needed. So that's how I'd approach this problem. It's worth appreciating the models and understanding the underlying concepts, even if the problem itself really isn't that difficult. Hope that helped. See you next time.